today's session, I would like to give you the complete information about the EV modeling from the scratch. So those who have not participated or missed the previous session, so today you can get benefit. So just allow me, let me start from the scratch. My machine taking some time, some more time. So just allow me, just be patient. So we'll take the previous data sets, sample data. So this is our sample data. From this sample data, we are trying to model it. Yes. Got it. Taking more time. Yes. Clear all. So now I'm trying to take so let me take the fresh window. Let us save this device. So I just saved as a EV half car model. And now the very first I select vehicle body. Yes. So this is our vehicle body. So if you follow the today session, then you can complete your project. You can complete your EV model completely. And tomorrow we will validate all your models. So now I would like to open the parameters of the EV block vehicle body. Yes. So now I have to now I have to feed all the data from here. Yes. So this is the data. So take the parameter window, and this is like a simple sample data to match the MATLAB requirements, right? So 80 plus 237 is the weight, and since it's a half car model, I would like to connect a single wheel per axle, and horizontal distance from the CG to front axle like 1520 mm. And a similar way for the rear axle also like 1400 mm, and CG height about 254 mm, right? And drag, the frontal area is 1.33 meter squared, and the drag coefficient is about 1.2. It's a constant. So now let us take this one. Yeah, so now we have configured as a vehicle body. So now let us take a tire block. So the tire block, try to use Control R to rotate the component. And here in the vehicle body, NR denotes the force transfer port to that wheel, and H denotes that hub of the vehicle. So now just open the tire. and take a constant magic formula coefficients, and geometry, select a inch, and take a 9 inch as a radius. And by default, the rolling radius will be, resistance will be turned off. So just enable it and apply the value. Yes. So now same way, just to take, use that right click and then drag the component, you may get a additional, wheel for the front axle. So now we have connected, and here in the vehicle body, W and beta used to configure the terrain input, wind input as well as the terrain input respectively. So to configure the wind input and terrain input, terrain information. So like terrain, our terrains are not a uniform terrain. So there will be ups and downs. So for that, we'll take a PS constant, use Control R, connect. So by default, the MATLAB will recognize instead of degree, so we will take a radians and 0 degree. All right. So just apply that one 0. Flat terrain. Let us consider the vehicle we are going to operate in the flat terrain, flat road. And the same way, the wind. So uniform wind, take a meter per second. Unit is the meter per second. And you can here you can apply a ideal. There is no any opposite wind velocity, right? And just to take a scope block to view the speed results. To verify the speed results. So straight away we cannot connect the Simscape component into the vehicle. So now take a PS2 Simulink converter and yes. So PS2 Simulink converter, and from that so now the vehicle model has been configured, and now just to take a solver configuration for adding as a header file, right? So this experiment we already modeled in the day 1 session. Now we would like to add the motor to this model. So just to take a DC motor, and take a equivalent, instead of equivalent circuit, take a by road rated load and then speed. And speed 2000 RPM, and rated speed should be 1500, and 3 kilowatt, and 100 voltage. Okay, so here just take kilowatt, and just apply to this block. So now we connected a motor block. So the motor shaft needs to be connected with the tire axle through the simple gear. So now you can connect. And the simple gear, we are trying to use like just the ideal component. There is no any speed reduction or increase, and the same along with the speed direction too. And take a mechanical rotational reference. Take a mechanical rotational reference. And now we would like to have a hutch bridge so that we can control the speed of the machine, right? For simple understanding purpose, the voltage, DC voltage is inbuilt one. So now take an internal power supply and averaged model. So for simple understanding purpose, so you don't have to worry about what is the duty cycle and all other instantaneous graph. So now we have a ready-made block sets to create a averaged output to the motor. And bridge parameter, keep it 400 as the maximum voltage. Right? Now, take a PWM controlled voltage. Controlled PWM voltage. So these are all the components to implement the speed control block. And now connect these are all the ground pins. These are all the ground pins. Just connect this ground. Now we may require to configure so here you should configure like a 5000 hertz, and then PWM is averaged block, and then input scale 0 to maximum, and output will be like 400 the maximum voltage. And now we have to configure the this one is the reference voltage for the accelerator, and this is the reference I mean what a reference voltage for the braking mechanism. So for that one, just take a controlled voltage source. Yeah. Now I would like to connect here. Same way, connect like this. So now this voltage will be the I mean what you can imagine that in your home the fan can be the ceiling fan can be controlled with the help of the potentiometer, which is that fan regulator. So similar way, we are trying to operate the vehicle with a single input from the driver. So that is as an accelerator, right? Now take one constant value and PS Simulink to PS converter. So these are all simple data conversions, not a big deal. This is a simple format. And same way, here. Now we are not applying the brake, and we are applying a maximum duty cycle 5%. Right? And here we have to connect the electrical reference. Is it clear, participants? Do you have any questions? Do you have any questions? Participants, do you have any questions?
Only thing is that we'll require some specifications of all blocks.
Yeah, I will give.
Okay, sir.
So you can easily get the information. Now you got all the component name, right? You can get all the component. So I just simplified all the circuit connections.
Excuse me, sir. Sir, can you repeat the vehicle's body's parameter?
Here the vehicle body is, this is the sample data. Right? So in the sample data, this is the weight of the vehicle and these are the dimensions.
Yes, sir.
Yeah, see here, total weight of the vehicle and the number of axle per wheel, so number of wheels per axle, and dimensions, generalized dimensions, like from the, front axle from the center of gravity and the rear, same way for the rear axle.
Yes, sir.
And this is the ground clearance. And after that, drag, how much drag, like a drag, nothing but like a frontal area, drag coefficient, all those stuff. And in the motor, this is the tire mechanisms, right?
Yes, sir.
This is what. We will share the information in the chat box so that you can practice by your own. Yeah, I just share the first level data. And after that, tire data. So here we have to change at the same time rolling resistance also we have to enable it. Right? So take a and magic formula, take a copy. Please practice the content of participants, then only you will get a value addition. Geometry. Yes. So now we have model. Let us try to run this for a few moments. So let us observe whether the vehicle is moving or not. Current controlled source 1 not yet connected. Okay. So here we have to change, instead of current controlled source, we have to change the voltage, controlled voltage source. Controlled voltage source. Yes, this needs to be more, not a current. So now let us try. Still there is a bug. Okay. Let me decode. Give me a time. Let me decode the value. Then I will. For voltage source only, I selected. So now I just modify the value. Yes. test check. Okay, yeah. So now the bug has been fixed. So let us open the, let us see the results. Yeah. See here, the speed has been when the motor vehicle started to rotate. I'm trying to increase the 100 seconds. Let us check how the vehicle reacts. Yeah. So this is the very first level output. And now I am trying to apply a brake after the 50th second. After the 50th second. How it can be implemented. So for that, there is a small information. Take a step input. And so this will be available, the 5 will be available for 0 to 50 seconds. And the brake will be applied at the exactly at the 50th second. So now, step time 1 initial value will be, initial value will be 5 and the final value will be 0, right? The step time 50 seconds. And in similar way, you take step time 50, initial value will be 0 and final value will be 1. Final value will be 5, right? So now just remove this one and interconnect the component. So now let us check. Yes. See here the vehicle started to decrease the speed from its original position, right? Exactly at the 50th seconds. So similar way, we have to verify. Earlier we did only one, only one model, and after that we have included the power electronic circuit. Now we included how to run the vehicle in the motoring as well as how to run the vehicle in the braking mode, right? Is it clear? Do you have any questions, participants? Participants, do you have any questions?
Good evening, sir.
Yes, madam.
So it is it is too fast to catch the block diagrams or model. So can you share this only today's video only?
But just a practice, ma'am. Then we'll take. We'll
Yeah,
check.
I know, but I think this is very important as compared to other days.
Yeah,
So
of course,
I
sir.
think if you provide this today's video only, so it might be very much helpful to me.
Yeah, so you just talk with our organization team. They will help you in if any possibility.
Okay, thank you, sir.
But I recommend you. I'm giving you in the session all the information.
Sir, I got it, but the problem is there, but some of the blocks are not in my Simulink model. Okay, this is the big issue. So
Okay.
I'm searching and finding, I got the point that first you just provided the PWM controller, then inverter, then DC motor, then you provided the machine, I think vehicle part.
Yeah.
I could not understand after the simple gear, what is that part? I think vehicle part might be.
So this will be the vehicle part. This is what we prepared on the day 1 session.
Okay, so what is the middle one? Actually, in the red block.
This one.
Yes.
So see
Wait.
here, the name has been.
It's a vehicle body.
Vehicle body it is. Yeah.
Okay.
And this is
So
the,
is it available in the Simulink model, na?
yes, everything is available in the Simulink. So I
Right.
got these block from the Simulink only.
Okay. Sir, in the as you told, that's one is the motoring action and second one is the braking operation. Okay. So in motoring operation, we are getting
This is the braking operation.
yeah, but what about the curve? I would like to know the curve. Can you discuss about the earlier one in motoring action and the braking operation? That means after 50 seconds, the motor will be stopped.
Yeah, correct.
Okay, in the previous one,
Motor,
actually I missed that graph.
vehicle will get stopped. So here we applied a brake. So you see here, this is the brake signal.
Hmm.
This is the brake signal. So
Fine.
the signal will be so here we are trying to apply a 5, right? That is maximum duty cycle at exactly at the 50th second. And so this is the initial PWM. So see here we applied the 5, that is the maximum duty cycle at the 0th instant till 50th second. Okay. So now this is called the accelerator, and at 50th second the driver will apply a brake. This is the open loop. This is the open loop configuration.
Okay, if we are interested for closed loop, so where to sense? Can we sense the speed of the vehicle and provided as an input to the PWM? Is it possible?
Of course, that's what we are trying to do.
Okay.
So now what happened? So now, just a second. Take a vehicle speed. Take a vehicle speed, right? And so here one control logic you may require, as the block name is Longitudinal Driver Block.
Sir, what is the function of this block?
Yeah, I will explain you. So let us take the block. The block will generate an appropriate acceleration command as well as the deceleration command based on the vehicle reference input as well as the actual input.
Okay.
See here, we are taking the vehicle reference feedback as the actual vehicle feedback.
Fine.
Right? Now we are generating an accelerator command through this, and this is the deceleration command. Right?
So you are using two voltage control, and one is for motoring and another one is for braking.
Yes, this is the simplified block sets to generate. See, actually in your house, how you are controlling the fan, your ceiling fan. So
by
you
regulator.
Regulator, right?
Yes.
Similar way, we are trying to model as a regulator.
Fine.
Okay. So here we will generate a 5 voltage maximum. Okay. If we generate 5 voltage, then the PWM intended to reach 100%. If you reduce the 5 voltage, then the PWM reaches to the 0 voltage, 0%.
Okay, sir.
Right?
Yes, sir.
Okay. So now we have to feed the reference input. Right? So take a drive cycle. Take a drive cycle source. So this is the drive cycle source. So earlier we used simple constant data to the vehicle's speed. Now we are trying to give a data set as like as the driver. Suppose if particular driver vehicle in the urban area. So sometimes it may require a high speed. Sometimes they will apply as a low speed and then brake. All the stuff will be applied, right? So now we are trying to create the same scenario and update the simulation time. So we have to run the simulation until that drive cycle get closed. So just up, right? And here the grade nothing but the upgraded. So you see here in the vehicle body also one beta port is provided. So here what we are trying, here we are trying to model the terrain. That similar way, here also the terrain input, here also you can configure it. Take a constant and for understanding, for simple understanding purpose, take 0. right? So now the vehicle is controlled with the help of one closed loop controller called PI controller, right? And I take the default PI controller values, but in the real time, we have to go through all the KI KP configurations. So now, I would like to run this model until the maximum simulation time, right? So I have to monitor what is the vehicle current value and then reference value, right? So now let us try to run this one. Yeah. So now let us change slightly modify the scope so that we can see the responses in very clear manner. So now this vehicle is responding for the driver input, right? So now let us analyze this graph. The red color denotes the ideal reference input, right? And the blue color denotes that reference output, vehicle responses from the controller, right? So let us take this scenario. So let us take this scenario. See here, the peak acceleration input has been given to the vehicle. Here, the zero acceleration command has been applied. So vehicle responds for this input, but it not meets it. The vehicle does not meet the zero instant within the particular time period. So what we have to do? So we have to improve the controller. So the controller nothing but this is the controller, right? If you open the controller, there will be a PI coefficients. So if you apply a proper PI coefficients, then you can get a what? So proper, you can get a proper speed responses, right? So by implementing such kind of applications, you can able to analyze and you can able to improve the performances of the electric vehicle. So now let me introduce one more part. We have selected the H bridge as the internal sourced voltage, right? So for that one, take a battery block. So in the EV without battery, how we can model it? So take a battery block, and here we interconnect the current sensor. Just remove it. Yes. And take a controlled current source. Rotate it. And here also again take a current source. And interconnect. Take a 100 voltage. And by default, it will be 50 ampere. Take electrical rub. Right? So how much amount of current we are trying to draw from this ideal battery? Whatever the motor draws, the same current we are trying to draw. Right? So now we have an instantaneous current from the battery. And how to implement the SOC block? That is that in your vehicle, the SOC data needs to be should be available, right? For that one, take a gain block, whatever we practiced in the previous one, and 1 divided by 50 into, like, let us take 3600 or 2474. So I take 3600. That is 1 hour we are trying to drive the vehicle. And take a discrete time integrator. And take a Simulink, PS2 Simulink converter. Interconnect all the components like this. And subtract from the, SOC minus 1. SOC of, initial stage of the SOC. So now take a sum block, subtract the instantaneous value from the reference one. So just add this one. Right? And take a scope. So this is what we are trying to model as a SOC block. So just to create a control G, and this is the SOC. That is the this data will be available on the dashboard of the driver. Right? So let us try to. Yes. See here, we are driving the vehicle for 1 hour. So this is the SOC data. So this data you can connect to the driver setup. So this is the SOC meter. So like that, you have to build your own EV and practice this experiment and do the mistake. So we can learn the concepts through the mistake only. Just do the mistake and post your mistake, post your errors screenshot into the group. Let me prepare the content, and then tomorrow class, we will address all your queries. Right? Is it make sense?
Sir,
Yes, madam.
hello, sir.
Yes,
Show
madam.
the display result, sir. This is scope result.
Yeah. Here you can compare that one. Let me take something. For simple comparison purpose, I'm just multiplying the signal with existing one, right? Since this range is 0 to 25, so I'm trying to add this one, multiply the value with the 25, which means that, right? So once if you started the vehicle, that time the battery has a full SOC, and after that, based on the driver vehicle responses, the battery got drained. Right. Similar way, you can develop your own applications. Do you have any doubt?
Sir, is there any recharging of the battery in this case, in the model developed?
It is possible. We can add that block.
Oh. Sir, in real time, the brake and application and the actual instant at which the vehicle stops. How much is the time, sir? That is possible, minimum possible now.
In the real time, so here we are applying the electrical brake. Okay. Real time, electrical brake will take time to reach zero position. So to address that one, we'll keep disc brake for all the wheels.
Okay.
As like the current IC engine vehicle having, right? The similar brake will be provided.
Okay.
Then
That means electric brake is not sufficient.
It won't help for the instant stop.
Yeah. Okay, sir. Okay.
Take some time. Because the moment of inertia will be available on the object, right? So yes, I hope you got complete simulations. So please try to practice this experiment. I am here to help you. Do the mistake. Why hided the SOC? See, no, actually, I have not hided the SOC. I just made one simple block in the, in the vehicle. You are not seeing the electronic circuit, right? So only the display only you are seeing. So similar way, like I just model it. Yes. Do you have any questions?
Sir, hello,
yes.
sir.
Yes, madam.
Testing and all, if it is to be done for model.
Come again?
In real time, we go for testing the vehicle, sir, for various tests are there, no? Likewise, can we do it for the model?
Yeah, we can do that testing also. Wherever, see here, instead of this battery, we can keep one more battery is there. Yeah, this is the table-based battery. Yes, I think so. No, the thermal. One more battery. Yeah. After this one. One temperature battery is available. Yeah. See here, you can assign the battery temperature, and you can configure the battery current and battery voltage. Like that, you can model it. This is one battery testing you can do for the driving pattern. And the similar way, the power electronic circuit also you can test. You can model one. What a THT values is, and then you can identify the vehicle motor torque performances. All those stuff you can do.
Thank you, sir.
So I will share this design in the chat. So please practice, make mistake. Through the mistake only you can easily learn. So if you have any questions, please prepare the question, and then in the tomorrow session we will discuss in detail, and we'll get control.
Sir, one small request, sir.
Yes, madam.
Sir, actually, can you expand the SOC, sir? You made a subsystem, sir?
Yeah, simple subsystem, madam.
Subsystem and all okay, sir. If we expand it, then it is we
so
can
that's
do
what we
easily.
discussed in the that's what we discussed in the previous session.
Sir, you're sharing the image in the chat box, sir. Instead of that, can you
Hmm.
able to share the same thing in your group? It is especially created for EV system, no, sir, for workshop
Madam,
FTP.
actually, this session is like a simple, we are just playing a simple mind game, right? Those who are participating in the session, see, since you are putting your valuable time for this class,
Sure, okay.
so
That and
that,
all very
that
smaller size, sir. I can't able to extract the real image, sir. That's why.
simply you just download it, keep it in your desktop.
You shared the image
Uh,
in the chat box.
uh.
It is difficult for me to extract, not extracted, to see in the full view, sir.
See, I'm getting the full view. See,
Sir, you are having the system with you. That's why you are enlarged
okay.
contrast. We
So you are
can't tell,
looking
sir.
with mobile,
No, system itself, sir.
Okay, then no, the system will get it. No, madam. Okay, so this image I will share it in the WhatsApp group. So please use that one. So let us check.
So I need SOC also, sir, because
Yes.
I strong in battery management. But
Okay.
I want to know how to do in all those
See,
things. And
see here,
I will make a screenshot.
we are trying to model one simple Coulomb count method,
Okay.
right? So this is the initial stage of SOC, right? SOC T minus 1th state. That is the initial state, right? So this is the I divided by C. That is a full capacity along with the timing interval, right? So we are running this simulation for 3600 seconds. That is 1 hour because our simulation time for 2500 seconds, right? And this is simple integrator, discrete integrator. And this value will be 1 by C, and then integral part of, I mean that unit will not be added here, integral part of current with the time domain, right? So this is the actual current drawn by the load. And here we know that we assume that the battery has been has a full charge at the 0th instant. So now we are subtracting the instantaneous value from the previous data. So what will happen? Automatically, we may get a balanced data, right? So this is what simple Coulomb count.
Okay, sir.
Sir, I have done the RC circuit. I want to share it.
Come again, madam?
RC is that Simulink, which I am not getting. This one, sir.
RC
Yes, sir.
for battery.
Yes, sir.
So that you have to model with the table, madam, as a table. You can use the table-based. With this one, you can see the what is that resistance along with the capacitance. You can add. This is the RC net table, lookup table.
Hello, sir.
Yes, madam.
And then how to make that SOC, sir? What is the step?
First, you have to measure the actual current, which is drawn by the load, right? And the first step, you have to implement that current, instantaneous current divided by the capacity, total capacity of the battery.
Sir,
So
this
here,
I understood. Sir, 1 minute. This I understood. You converted this circuit into a block, sir. That's what.
No. That one is simple, ma'am. So just
Uh-huh.
select all the block.
Okay.
Just select all the block and go to the right click, create a subsystem. Or else click Control G. That's enough.
Okay, sir. Okay, thank you.
Thank you, Madhu. Right. I hope I have given you all the informations. Please practice this experiment and come up with your doubt. I'm very happy to answer your all the kind of doubts and get involved in the EV design.